In the silence of the cosmos, a profound mystery beckons. Beyond the stars, beyond the galaxies, there lies an unseen force, a force that governs the very structure of the universe. This force is as invisible as it is essential, and though it makes up most of the universe's mass, we cannot touch it, see it, or even directly measure it. And yet, it shapes everything we know. It binds galaxies together, bends light across the vastness of space, and holds the very fabric of the universe in place. This elusive substance, known as dark matter, is the silent architect of the cosmos. But what is it? How can something so crucial remain so hidden? This is the cosmic mystery of our age, the search for dark matter. We know of dark matter's existence, not by direct observation, but by the way it bends the rules of the universe as we know them. Imagine, for a moment, a galaxy spinning. The stars within it swirl in a delicate dance around a center of gravity. If only the visible matter, the stars, gas, and dust, were at play, we would expect them to orbit the galaxy's center much more slowly. In fact, based on the mass we can see, galaxies should be tearing apart, their stars flying off into the void. But they do not. They stay bound together. Something unseen, holds them in place, and it is this unseen mass that we call dark matter. And it's not just one galaxy. In galaxy clusters, where hundreds or even thousands of galaxies are bound together, the same phenomenon occurs. The gravitational effects of dark matter extend across vast distances, ensuring that galaxies move together despite the forces that should pull them apart. Without dark matter, the universe we observe would be an entirely different place. Galaxies would be much less stable, and many would never have formed at all. Dark matter is, in many ways, the invisible scaffolding of the cosmos, holding everything in place. Yet, despite its gravitational effects, dark matter remains utterly invisible. We cannot see it with a telescope, nor can we detect it with traditional instruments. It does not emit, absorb, or reflect light in any way that would reveal its presence. This makes dark matter incredibly elusive. Its existence is known only through the gravitational influence it exerts on visible matter. It is a phantom, present everywhere, yet never directly observable. And so, scientists have been forced to seek out the faintest whispers of dark matter, tracing its movements, calculating its effects, and searching for traces of it in the most unlikely places. One of the most intriguing ways we've come to detect dark matter is through gravitational lensing. Imagine light traveling across the vastness of space, only to be bent by the immense gravity of an invisible object. Dark matter acts like a lens, warping the path of light from distant stars and galaxies, creating visual distortions. These distortions, though subtle, reveal the presence of something massive and unseen. By studying the way light bends as it passes through galaxy clusters, scientists can map the invisible presence of dark matter with surprising precision. In this way, dark matter becomes visible, if only through its gravitational fingerprint on the light around it. For decades, scientists have been building increasingly sensitive instruments in a race to detect dark matter directly. In deep underground laboratories, far from the interference of cosmic radiation and the noise of the Earth's surface, detectors are waiting, poised to capture the faintest signals. These labs are a battleground, where scientists try to catch a glimpse of dark matter particles, those elusive, hypothetical particles that are thought to pass through everything unnoticed all the time. These detectors are designed to pick up the faintest tremor caused by a dark matter particle colliding with a regular atom. But so far, these particles have proven remarkably elusive. In parallel, high-energy particle accelerators like the Large Hadron Collider are also playing a critical role in the search for dark matter. By smashing particles together at near the speed of light, scientists hope to recreate conditions that could produce new, exotic particles that could explain dark matter. In these powerful collisions, researchers look for telltale signs of dark matter, hoping to capture it in the act. But for all their efforts, dark matter remains stubbornly out of reach. It seems as though it has been hiding in plain sight for all this time, evading our best attempts to unmask it. It is staggering to think that something we cannot see or touch, something that has no interaction with light or ordinary matter, forms the backbone of our universe. Dark matter is not just an anomaly. It is a cornerstone of the universe's architecture. Without dark matter, galaxies would never have coalesced, and the cosmos would have remained a far more chaotic place. It is, in essence, the invisible glue that holds the universe together, forming the vast cosmic web that connects galaxies across unimaginable distances. To understand dark matter fully, we must turn our gaze backward to the very origins of the universe. In the moments following the Big Bang, the universe was a hot, dense soup of particles. It was during this time that dark matter first began to play its crucial role. As the universe expanded and cooled, dark matter clumped together under the force of gravity, forming the seeds around which the first galaxies would later grow. It was these clumps of dark matter that gave rise to the first structures in the universe, allowing galaxies, stars, and eventually planets to form. Without dark matter's gravitational influence, there would be no stars, no galaxies, no Earth, no us. Dark matter is not merely a footnote in the story of the cosmos. It is the unsung hero of creation. But the true nature of dark matter remains one of the greatest puzzles in physics. The cosmic microwave background, CMB, the faint echo of the Big Bang, has provided one of the clearest pieces of evidence for its existence. By studying the CMB, scientists can trace the distribution of matter in the early universe. Dark matter's presence is felt in the way it shaped the universe's initial expansion and in the ripples left in the cosmic fabric. These subtle imprints are like fingerprints, showing us where dark matter once existed, shaping the universe even before the first stars lit up the skies. Though we cannot directly observe dark matter, we can study its effects with remarkable precision. Advanced simulations show how dark matter interacts with ordinary matter, guiding the formation of galaxies and clusters. These simulations reveal a universe teeming with invisible structures, massive clumps of dark matter that govern the growth of galaxies, stretching across vast distances. Each simulation brings us closer to understanding how dark matter works, but it also raises more questions than answers. In the end, the search for dark matter is not just about discovering an invisible substance. It is about uncovering the very nature of reality itself. Dark matter holds the potential to revolutionize our understanding of the universe. It could be the key to understanding some of the most profound mysteries of physics, such as the nature of gravity, the behavior of the fundamental forces, and even the possibility of other dimensions beyond our own. It challenges everything we know about matter, energy, and the fabric of space-time. The search for dark matter is, at its core, a search for the unknown. It is a journey into the invisible, a pursuit of knowledge that stretches the limits of human imagination. As we look to the stars, to the galaxies, and to the vast stretches of the cosmos, we are reminded that the universe is full of mysteries yet to be solved. And perhaps, In the darkness of the unknown, we will find not just the key to dark matter, but the answers to questions we haven't even thought to ask. The universe is a grand mystery, and dark matter is the greatest riddle within it. But perhaps, just perhaps, the truth is closer than we think.